For my computer graphics project, I decided to recreate this piece of promotional art for Portal 2's co-op campaign. While the scene is pretty basic, with only a handful of different materials, my decision was heavily influenced by the presence of the portals, as I was really interested to see what effects I could create with the light emitted from them. One thing that really helps the images is that I was able to find a rigged P-body model on Sketchfab. This is the taller character. The skeleton was made incredibly well, as everything down to individual pistons was adjustable. Although Peabody's position is not perfect compared to my reference image, it is very close. Unlike Peabody, there were no rigged models for the other character, Atlas, that I could find. However, I came across one model which had Atlas in a similar pose to my reference image and was able to use that. Both models are referenced at the end of this video and in the description. First, let's take a look at the result of my rasterizer. The image looks relatively basic, partially due to rasterization not being very effective when it comes to portraying realistic lighting. The colour for each pixel is calculated by converting each vertex's world space coordinates into camera space and finding the vertex's face normal from the cross product of two vectors in the face. This value is then normalised to produce a unit vector and the shading of each face set to the dot product of the face normal and view direction. An if statement checks if this dot product has a value greater than or equal to 0, and only continues to set a colour if this is the case. If the dot product is less than 0, no colour is applied and the face is culled. Within the if statement, the dot product of the shaded normal and view direction is calculated and assigned to n.view. Colour is applied to each pixel by setting its RGB values to this dot product, multiplied by a number up to 255. These numbers are hard-coded and depend on the model, determined through a switch statement. For example, the far portal's red, green and blue values are n.view multiplied by 255, 93 and 0 respectively. This could be considered to be foundations for texture support, which I believe could be implemented by setting the pixel's colour to the colour of its corresponding UV coordinate, multiplied by the n.view value. However, I haven't looked fully into this. Before backface culling is implemented though, there is also hidden face removal using a Z buffer and barycentric coordinates. If the current triangle is closer to the camera than another triangle in the same coordinate in screen space, then this new triangle overrides the data of the previous one. This data is contained within a depth buffer, which is an array the size of the total number of pixels in the image. I also looked into applying multi-sampling anti-aliasing, which seems like it would require utilizing the frame buffer to hold data from subpixels, then averaging each pixel's subpixel colors, but evidenced by these renders, I couldn't quite figure it out. The main downfall of the rasterized image is the absence of light emitted from the portals. As a result, this version of Atlas and Peabody are probably thinking they'll run headfirst into a picture of a portal rather than a real one. The ray-traced image is a much better representation of how lighting would behave in this scene. Specific materials have been implemented, inheriting from a base class which holds data such as the angle of a bouncing ray and the colour to be emitted. Each material has its own features such as shininess or fuzz for a metal material, or emitted colour for a diffuse light. In my scene, there is a metal material on the two characters and their portal guns, a diffuse or Lambertian material on the walls, ceiling and floor, and different emissive materials on the portals and main light source. A dielectric material was also created, but wasn't appropriate for any object in my scene. There is also a subtle depth of field effect in the scene, which is most visible when comparing the sharpness of the characters, especially on Atlas's right shoulder plate compared to Peabody. Another feature of the ray tracer is soft shadows. Looking closely at the floor around the character's feet, gradual changes in light levels can be seen, as well as some areas being significantly darker. One addition to the ray tracer that improves its quality is multi-sampling anti-aliasing, or MSAA. MSAA involves taking multiple samples within a single pixel and sending rays through each sample. The colours returned by each ray within a pixel are then averaged to give the final pixel colour. This reduces noise in the image, as only one sample per pixel would not be an accurate representation of how light moves throughout the scene. The final image was rendered at 500 samples per pixel, which significantly improves its quality. To help speed up the rendering process, I incorporated two acceleration techniques. One was multi-threading, although code related to creating a thread pool is sourced from Ryan Westwood. This code allows individual cores to work on individual rows of pixels simultaneously. The other technique was bounding volume hierarchies, or BVH. While BVH takes a while to build, usually around 155 seconds for my scene, it significantly sped up the rendering process in my case. With BVH, one scene at a reduced resolution and 3 samples per pixel took just over 3 minutes to render. Without BVH, it was still trying to render the first frame after 16 minutes, at which point I decided to stop the program. This wasn't the most in-depth testing by any means, but it gave a good indication that BVH had a very positive effect on render times. I experimented with adding an intensity parameter to the diffuse light material, which multiplied the output color by the intensity. However, if this caused a color value to exceed 255, pixels affected heavily by this light would return black instead of the intended color. This is clearly visible on the character's frames here. I also had an issue with the initial implementation of the Lambertian material, where it seemed to be producing reflections on what should have been a diffuse material. For example, you can see Peabody's reflection just to the left of the blue portal in this render. I increased the scatter direction of rays at an angle near or below 0 by 0.1 in all axes, instead of giving them the value of the face normal. While this does reduce the efficiency, as some rays may be reflected into the surface, the material proceeded to represent a diffuse material. Another issue I encountered was faces having no shading, seemingly when hit with a significant amount of white light. Interestingly, the models are not affected in the same way by the light from the 2 portals. I attempted to fix the issue in multiple ways, such as reducing the intensity of the light and reducing the light's color values. I had a theory that the different behavior could be due to the main light sphere shape being defined within the project's code, while the portals were imported models. Unfortunately, importing a spherical model and applying the emissive material to it produced the same result. Now on to PBRT. While the PBRT for Maya plugin is a bit awkward, its materials are incredibly accurate. Also, it was much simpler to add textures, so the walls, ceiling and floor are now all textured, which really helps make the scene feel more real. A huge positive of the PBRT technique is that the materials are very realistic, especially the metal material applied to the characters and their portal guns, which is a great representation. Furthermore, shadows are much clearer using PBRT, but this is probably a result of the lighting being brighter. The PBRT metal material is much more realistic than the metal material used in the Ray Tracer. This is also helped by the vertex normals showing correctly, even under intense light, unlike in the Ray Tracer. The biggest issue with the PBRT render of my scene is once again related to the portals. Firstly, the light they emit causes fireflies, and the material on the portals themselves have an effect not too dissimilar to TV static, which really hurts the realism of the image. This seems to be caused by the use of a PBRT Disney material on the portal models. One alternative would have been the PBRT diffuse area light material, however this material did not work as expected. So much so that after testing it on multiple different geometries, I believe it could be bugged, or I simply don't understand how to use it correctly. This is because the portals would simply disappear when applying the area light material to them, and no light would be emitted in the render, although I believe they actually are in an area of the scene that is not visible to the camera. While testing, if any light did appear, it had the exact effect I wanted, creating accurate reflections on the models, but I could not get this to work from the portals. This is why I decided to apply the Disney material, as it still emitted light and was actually in the correct place in the rendered image, even though it has its drawbacks. Another option to reduce fireflies in the scene would be incorporating Monte Carlo sampling, adjusting the weighting of the rays to find an optimal balance. This could be potentially implemented in future. Overall, I am fairly happy with how each render turned out, but there is plenty of room for improvement in all 3 implementations. I'll be looking forward to build upon each renderer in future. Thank you very much for watching, and enjoy the rest of your day.